Okay, thank you. We'll start today. Only 20 students are there. Myself 4 minutes late, but okay. Okay, guys, are you able to see my presentation slide? Hello?
Yes, sir.
Okay, today we start the new chapter. I mean, not new chapter, the same chapter. The powers the subtopic we not yet completed. So today we start. Just we started yesterday. We go in depth discussion today. Okay. Now power screws. I mean, you might have been seen in your life screw jack, right? I mean, screw jack, for example, power screw, power screw. I mean, what is the principle of screw jacks? Please, someone tell that how it is functioning. Any idea? Earlier we discussed threaded joints, right? The threaded joints we use to hold two components securely, right? I mean, that the threaded joint, whenever the components is going to have repair, then we are dismantling and we are modifying. If we need to modify the component, we have to dismantle the screw. I mean, threaded joint, right? We have to dismantle the nut and bolt for dismantling the component. That's our threaded joint we discussed that. But in threaded joint, I mean, we are not oftenly dismantling, assembling. Whenever required, it's the components we want to modify, we want to redesign, and any problem in the bolt and nut, then only we are doing that. But here, power screw is not like that. Now we are when I mean here we are operating for a screw jack. And if you take some mechanic shop, I mean four wheeler car mechanic shop, what they're doing, they're using screw jack continuously. I mean regularly operating the screw jack to lifting the vehicle for performing the service or maintenance of the car, right? So repairing the car. Then here we are oftenly using this the screws, right? Here also plain screws only, but we will see that what is the application one by one. We will see that today. Then we enter into the power screws. Now, power screw is a mechanical device used for converting the rotary motion into linear motion. Rotary motion into linear motion. Rotary motion into linear motion. Very important. Okay. Now, rotary motion into linear motion and transmitting the power. That is the application of the power screw. Now, the power screw also called as the translation screw, also called the translation screw. I mean, here, what kind of geometry we are using here? It uses a helical translatory motion of the screw thread. Helical translatory motion of the screw thread is transmitting the power rather than the clamping the machine components. I mean, we are not fastening the two components here. Only we are applying the force in the handle. For example, this handle, we are rotating the nut and that is screw moving up and down. The linear motion, the rotary motion, where we are applying the rotary motion. For example, here, the rotary motion we are applying here, that rotary motion converted into linear motion for lifting the vehicles, for lifting the components. Here we are not clamping in the components, we are lifting the component. Okay, that's what we are using. here this kind of helical translatory motion of the screw thread for transmitting the power rather than the clamping the machine components. Okay, now the main advantages, what are the main advantages? As I told you, that to rise the load or to lowering the load, for example screw jack, right? And to obtain the accurate motion of the machining operations, we are using this lead screws of the lathe. I mean, the lead screw, you might have been studied, right? I mean, the lathe machine working principle. The lead screw, when you are giving the off access, when you are accessing the lead screw, the automatic feed can be given to the carriage in the lathe machine, right? There we are using lead screw. That lead screw also under the category of power screw only, under the category of power screw only. And to clamp the workpiece, I mean vise, I mean we are using vise, the vise, no, the machine vise, the machine vise we are using power screw, machine vise we are using power screw. And universal testing machine, and the universal testing machine we are using power screw to down or up the I mean load arm, to down or up the load arm we are using power screw in the universal testing machine. Okay, I mean, now these are the things. And what are the main components in the power screw? Power screw, there are three parts. One is screw. I mean, one is screw. This one is screw. The second one is nut. This one, I tell you here. I mean, the one is screw. This is the main part. The second one is nut. Third one is, I mean, hold either screw or nut into the place where we are holding the screw and nut. This is the main part of the power screw. Main part of the power screw, right? Now, here I told you the two examples. I mean, now we are going to discuss. There is a two main examples. For example, first example, lead screw in lathe machine. In the lead screw lathe machine, the screw is rotating, the nut is moving along with the carriage in the lathe machine, right? That's what. The screw rotates in the bearing while the nut has axial motion. Axial motion. The lead screw of the lathe is an example. The lead screw is the lathe example is the power screw. An example for the power screw. Right? And the second thing, the lead screw, I mean, lead screw kept in constant. I mean, sorry, the lead screw, not the nut is kept in constant. The lead screw moving linear direction, linear motion. For this is screw jack. Screw jack, the lead screw moving linear direction up and down based on apply the load condition, either clockwise rotation or anti-clockwise rotation of the handle. The lead screw move up and down, right? This is a linear motion. The nut is hold on constant position. I mean constant position. So this is a two category. In lathe machine, the lead screw is a static. The lead screw is I mean not moving part. Only the nut is moving part in the lead screw. While while this power screw using in the lathe machine. But in the screw jack, the lead screw is a linear motion. The lead screw is a developed linear motion. The nut is in constant position. The nut is not moving part. Only moving part lead screw in the screw jack. That is important. Okay, now I mean power screw is I mean power screw has large load carrying capacity. It can be lifted for very large amount of load. It can be lifted easily. Okay, I mean then the simple construction, I mean the compact device, it can be easily carrying from one place to another place for lifting the heavy weight of the component, heavy weight of the component. Okay, now here we are using different types of screws. I mean the power screws, we are using different types of screws. For square threaded power screw, then I mean trapezoidal threaded power screws. Square threaded power screw can be made with a lathe machine, but a trapezoidal power screw can be made with the help of the threaded milling machine. Please understand, you may expect this type of questions in the objective. I mean, the square threaded power screw can be made with the help of the lathe machine, but trapezoidal threads are made with the help of the threaded milling machine. Threaded milling machine, how we are preparing this. Now I come to that power screw provide a large mechanical advantages. How we are saying large mechanical advantages? For here you keep the ton of weight in the top of the cup, the loading cup, then we are applying the few hundreds of newton. Here we are giving thousands of newton, thousands of newton, 20 kilonewton or 30 kilonewton, whatever, 40 kilonewton. But when we are trying to lift this weight 20 kilonewton or 30 kilonewton, only we are applying few hundred newton only through the handle. That's what it's a huge large mechanical advantages in the power screw. Okay. And large advantages and various applications, like screw jacks, clamps, walls, vice. We are using those places. In screw jack we are using power screws. Vice we are using power screw. Vice means to hold the component. We are using power screws, and walls we are using the power screws. Okay. Now the power screw gives a smooth and noiseless service without any maintenance. Smooth and noiseless service without any maintenance. Okay. And the another advantages it is for example, now another applications, the screw jack is self-locking characteristics is very important. Because while lifting the weight, to be hold the weight at a particular appropriate, our required time to hold the weight without lowering the weight, then the self-locking arrangement also can be provided here. Once I keep the weight here and I'm going to lift the weight for a few centimeters, after I'm holding the weight and leaving the power screw, I'm not applying any load, then the power screw able to hold the weight at our required time. That is called, then the self-locking effect is very important to hold the weight at appropriate height, particular duration, without lowering the weight. So that self-locking property can be provided in the can be provided in the power screw. Okay. Now power screw, the main disadvantages: less efficiency. The poor efficiency is one of the disadvantages. Another disadvantages is, I mean, uh, high friction in threads causes the wear of the screw and nut, because we are always trying to lift more weight using screw jack. For example, we are trying to lift more ton of weight. Ton of in 1,000 ton or 1,000 kilonewton, or 10 kilonewton or 15 kilonewton or 20 kilonewton force we are trying to lift. During that time, the screws between the nut and the screws between the the screw thread between the screw thread and the nut thread going to be a high friction, then high wear going to be created. Then it will be created high wear and tear. That is a major problem. Then when we are accessing multiple times, due to wear and tear, this is going to be loosened this part. That is one disadvantages that cannot be avoided. But instead of that, we can change the material. For while you are lifting them, lifting the weight, more weight, and when we are accessing frequently this screw jack, for example, then we have to go for high hardened material, then the wear and tear it may be avoided. Okay. So these are the disadvantages. Now in these power screws we are using different types of threads, very important. Different types of threads. What are the types of threads we are using in the power screws? So one by one we see here. Now see here, V threads we are not using. See here, i mean we already discussed V threads. The V thread, what is the use of V threads? V threads mostly we are using for fastening two components, fastening the two components or joining the two components, because V threads creates the more frictional torque. V thread creates the more frictional force. Yeah, that's what. 1 minute, I draw a simple diagram. V threads, this is the two component to be joined securely. We are using the V threads because V threads creating the more frictional force. This is the V threads we are using. Bolt and nut. Okay. Now this is the V threads we are using for his, sorry. Okay, here we are using to join the two components or fashioning the two components. This is a component to 1, this is a component to 2. I mean, this is for long duration to hold the component. We are using V threads because V threads develop, because the another side we are going to use the nut. The nut will develop the, I mean, then here it will be develop the high frictional force. This is, here we are using V thread. But here, in this case, in our case, we can't use the V threads because, I mean, here we need more frictional force. Otherwise, if we reduce the frictional force, the component going to be loosened, right? But in our case, in power screws, we can't use V threads because here it will be increased more frictional force, then we cannot increase. For example, if increase the more frictional force in this region, we unable to lift the weight also. Then appropriate frictional force only we have to maintain. Hence, V threads we can't use in our applications, in our power screw application. Now, only we are using, there are different, mostly we are using this type of threads: square threads, trapezoidal threads, ACM threads, and butters threads. I mean, this is briefly we discuss each and every one. Then you can understand, you can get more clarity about this type of threads. Okay, now see here. V threads only use, V threads cannot be used for power screws because, I mean, we don't like to high frictional force. Frictional force, okay, and screws with a smaller angle, screws with a smaller helix angle, that can be used for our application, power screw application. Now see here, this is square thread, trapezoidal thread, and here the pitch, this is the, I mean, the every dimensions also given. P is nothing but a pitch by 2, that mean height of the screw, height of the thread. Okay, now this is the width of the height of the thread, this is the pitch of the thread. Okay, here this is the high, here the angle, helix angle is 30 degree, and ACM thread and trapezoidal thread are almost same only the helix angle is little different, 29 degree. Here the helix angle is 13 degree. Anyway, we will see one by one. I mean, we are using the two popular types of threads. One is square thread, another one is, I mean, using popular, so one is square thread and another one is isometric trapezoidal threads. One is square thread, another one is isometric trapezoidal threads. These are the popular thread type using in power screw applications. Power screw application. Okay, now see here, I mean, the efficiency, we are comparing the square threads and trapezoidal threads. See, the efficiency of the square thread is more than the trapezoidal thread. And another very important point is that there is no radial pressure and side thrust in the nut. I mean, while using square thread, there won't be a no radial pressure and or radial thrust on the bolt nut. I mean, suppose this is our nut. This is our nut. If I am using here square thread, there won't be a radial pressure or radial side thrust on the nut. Side thrust on the nut threads. Side thrust on the inside the nut. And that is one of the best, one of the advantages in the square thread. Okay, this you may expect this type of questions in your objective, even competitive exam also. So in now one more time telling that square thread, it won't be a radial pressure and it won't be a side thrust in the nut while using square thread in the power screw applications. I mean, this radial pressure also called, I mean, also you can say that bursting pressure. The radial pressure is nothing but bursting pressure. Bursting pressure. Here, I mean, now another thing, that is the uniform motion can be obtained while using square thread. While using square thread, uniform motion can be obtained. The life of the power screw can be improved, increased, or improved or increased. Now I come to these disadvantages. I mean, the square threads difficult to manufacture. Okay, now the strength of the square thread is less than the trapezoidal thread, because see here, I mean this thread width, that mean width of the thread is less than that trapezoidal thread. Now which thread is more with more thickness, that thread it will be withstanding more strength, more load also. Hence the power square thread is, the strength of the square thread is less than the trapezoidal threads. Now I can trapezoidal threads. Okay, and now this is a very serious problem in these square threads, because it's a more wear and tear. I mean this is square threads. So now I have to, this is enough advantages and disadvantages about square threads. Now come to the trapezoidal threads. Trapezoidal threads is the manufacturing with the help of the, I mean the thread milling machine. Thread milling machine. This is with the lathe machine. This is manufactured by, we mean manufactured with the help of the thread milling machine. Thread milling machine. This is the, we are using. We can use multiple cutting tool for making this thread arrangement. Hence, the cost of manufacturing is less in the trapezoidal thread. And the trapezoidal thread has a more thickness. I mean, this is, I'm telling that this thickness, this is a T, I mean this is maybe T, this thickness is T1, this is a T1, the T1 is greater than T, hence this strength of the thread is more as compared to square thread. Trapezoidal thread strength is more. Okay, now stronger than the square thread. Now I come to the, what is the ACM thread. Some more examples. I mean, what is the disadvantages of the trapezoidal thread? I mean, few points. The efficiency of the trapezoidal thread is less than the square thread. The efficiency trapezoidal thread. This is efficiency square thread. This is efficiency trapezoidal thread. The efficiency of the square thread is greater than the efficiency of the trapezoidal thread. This is less. This is the disadvantages. Okay, and very important here, the radial thrust, or I mean radial pressure will be there. Side thrust or radial pressure. Side thrust, sorry. Radial thrust or side, I mean radial side thrust, sorry, side thrust or radial pressure cannot be avoided in the trapezoidal based power screws. Okay, trapezoidal shaped based power screws. Here radial pressure and side thrust always should be there. In square screws, so I mean square threads, it won't be there. Okay, that is the main disadvantages. Now I come to the ACM thread. ACM, as a mechanical engineer, you should understand this type of threads and what is the advantages, what is the disadvantages. Now ACME threads, the helix angle in trapezoidal threads 30 degree, but I mean in here, I mean the 29 degree. The trapezoidal here the helix angle is 29 degree, but the application both are similar. ACME thread and trapezoidal thread both are same only. Now I come to the buttress thread. I mean buttress thread is combination of our, I mean square thread and trapezoidal thread. Please understand, this is the buttress thread is a combination of square thread and trapezoidal thread. That's all. And the buttress thread can be used for heavy force lifting component. Buttress thread used for in the screw jack, where we would like to lifting heavy force, that place we can prefer this buttress thread for making our power screws. Okay, buttress thread can be used for heavy axial force, for lifting the heavy axial force, but it will works only one direction. This buttress threads, it works in only one direction. That is the one of the disadvantages. Okay, but this is a buttress thread is a higher efficiency compared to the trapezoidal threads. I mean, that is what is the order of the efficiency now. Order of the efficiencies. Square thread is better than trapezoidal thread, right? But here this is better than trapezoidal thread. Then order of the efficiency, square thread is greater than, I mean, buttress thread efficiency. Buttress thread efficiency greater than trapezoidal thread. That is order of the efficiency of this thread. Okay, this is a buttress threads. I mean, it can be accessed at only one direction. Only one direction only it can be accessed, this buttress thread. But the strength of the thread is more than the other two threads. I mean, see here, the strength I put here, the strength is, for example, the strength of the thread, this is a buttress thread greater than, I mean, trapezoidal thread, TR, this is greater than, I mean, square thread. This is order. You may expect this type of objective type questions. Okay, and I already told you order of efficiency also, please keep in mind. I mean, these are the types of threads. Finally, we come to the some conclusion about these threads. Okay, the butter threads, and means finally I tell you the few application of each thread. Okay, for screw jack can be used in press machines and clamping device. Okay, screw jack, I mean square thread. Sorry, square threads. Square threads can be used in screw jack, and also used in press machines, and also it can be used for clamping device. Okay, screw thread, square thread applications. And I'm now trapezoidal threads can be used in power transmission device in machine tools. I mean, trapezoidal threads especially we can use the power transmission tools in power transmission in machine tools. I mean, this is nothing but machine tools. Square threads, sorry, trapezoidal threads. I mean, square thread is screw jack and a press machine and a clamping device. Here we are using. Now the last one is, I mean, buttress thread. Buttress thread can be used in vice for one, mean can be used in vice, heavy holding vice. We can use buttress thread, can be used in vice, and where the heavy force to be transmitted, that place it can be used. But this is only operating only one direction, the reverse direction we cannot operate. That is the major disadvantage of the buttress thread. Now I come to the some, what I told you, that there are two important threads. I mean, basically we are classifying into square thread and isometric trapezoidal thread, right? Then based on this, I mean, international standards, they declared some table. We are following the table for preparing these threads. Now see, this is now nominal diameter of the thread, nominal diameter of the bolt, right? 22 mm, 24 mm, 26 mm, 28 mm. Then we have to follow this 5 mm pitch. Suppose now my thread nominal diameter is 55 mm and 60 mm, we have to follow the 9 mm pitch. Okay, now this is for normal size. Normal size, I mean square thread in normal size, square thread in normal size, normal series, sorry, normal series. Now when we are going for isometric threads, especially isometric thread is nothing but trapezoidal threads. Trapezoidal threads, the 24 mm diameter, nominal diameter D, then that should be the width of the thickness of the thread is 5 mm. 5 mm. For example, 60 mm it will be 9. Okay, I mean 60 mm it will be 9. 70 mm to 80, 70 and 80 it will be a 10 mm. 10 mm. So you can compare here. See here. Here even 55 mm we are following 9 mm thickness of the thread, but here only 60 mm only we are following this 9 mm. There are some more differences there. Please go through the table, you can understand. But this is a standard values. While preparing the trapezoidal thread and square threads, we used to follow these standard values. Okay. Now I come to the now come to the terminology of power screws. Terminology. What are the terminology we are using in the power screws? Now we are going to see that. Okay, terminology in the power screws. Now Now see here, what are the terminology? We are using pitch. See here, now I take another diagram. Okay, you can see here. This is a pitch. Where is what is a pitch? We already know. I mean, when we study the threads, the different types of threads, right? Crest to one crest to another crest, the distance is called a pitch. We already know, right? Now that is the this color is not good. I take this color. This is a pitch. Now, lead. What is the lead? I mean, what is the lead? While the one rotation of the nut, one rotation, how much the thread is lifted, the screw is moved. That is the lead. Now, this is the okay. Anyway, just this is very you can easily understand. Just I read this. Please go ahead later. Now, pitch is nothing but that is the distance between the thread corresponding to the distance between the thread. Okay, this is the thread corresponding to the point on the adjacent thread. I mean, corresponding point on the adjacent thread, or you can say that one. I mean, one crest to another crest, the distance between one crest to another crest. You can say the pitch. Lead is nothing but the distance measured parallel to the axis of the screw, which the nut well in advance in one revolution, how much the screw moved, the distance it will be measured parallel to the axis of the nut. Measured parallel to the axis of the measured parallel to the axis of the nut. That is now lead. Now I mean nominal diameter. Nominal diameter is nothing but a major diameter. That's what we already discussed. Even threads also major diameter is nothing but nominal diameter. I mean core diameter is a minor diameter. This is the plane. I mean, this is a core diameter. Now, mean diameter is nothing but dm plus, dc plus d by 2. dc plus d by 2, that is mean diameter. d plus dc by 2, that is mean diameter. See, this is the nominal diameter. Nominal diameter is the largest diameter of the screw. Larger diameter of the screw here. Larger diameter of the screw. It is also called major diameter. Core diameter is the smallest diameter of the screw. Smaller diameter of the screw thread. Core diameter. It is also called minor diameter. We already studied. I mean, helix angle. What is a helix angle? What is the importance of helix angle? Now we are going to discuss that one. Very important because, I mean, based on the helix angle only, we are going to discuss the. I mean, rising the screw jack and lifting and downing the screw jack. I mean, we are going to discuss later about that only. I mean, torque requirement while lifting the load, torque requirement while rising the load, that with respect to those operations with respect to alpha and I mean helix angle and friction angle. Helix angle and friction angle, those things we are going to discuss later. But here we would like to understand before entering in that, what is the alpha. Alpha is helix angle. The helix angle is defined the angle made by the helix of the thread with a plane perpendicular to the axis of the screw. Perpendicular to the axis of the screw. This is nothing. This is a perpendicular to the axis of the screw. Here we are considering the helix angle. Okay. Here we can't say, but clearly you can see here. Yeah, here very. Now see here, this is the helix angle. Now the helix angle, how we are finding the helix angle? Now you see here, the helix angle is a function of our dm and the lead. See here, the helix angle alpha is function of dm and lead. Lead is lead. Okay. Now see here, this is my horizontal, I mean distance here. Now I show you here itself, you can easily understand. This is okay. Now this is my L distance, right? Now this is my helix angle. Now I'm taking the bottom side. I'm considering our mean diameter. We are considering the mean diameter. Okay. I mean mean diameter here. I mean already we have been explained what is this a DC. DC is a core diameter. Core diameter is nothing but our, I mean core. What is the core diameter here? Core diameter is nothing but capital D minus here P by 2. Here P by 2. This side P by 2. This side P by 2 is there. This is pitch by 2, P by 2, P by 2. Now D minus P by 2 plus P by 2 is nothing but our core diameter. Core diameter, because this is a pitch, but here this pitch here, I'm saying here, this is here, this is our P by 2, this side P by 2, then subtracting from our major diameter P by 2 plus B by 2, we are going to get, it's nothing but a P. D minus P is nothing but our core diameter. D minus P is our core diameter. I erase this. We are already given clearly. Okay, D minus P. D minus P is nothing but our core diameter. Now, what is the mean diameter? I mean, D plus our major diameter plus core diameter divided by 2 is our mean diameter. Now, I mean, the mean diameter can be written here in terms of major diameter. D plus D minus P. The D minus P is nothing but our DC. Okay, our DC. Now, from this, because I need mean diameter to find out my helix angle. Okay, and now I know what is the lead, how much distance to travel to my nut, now my screw at one revolution. That is the lead. Now, I mean, now the lead is nothing but the lead divided by pi dm. Now this is the mean diameter at one revolution, hence I am putting pi dm. Pi dm is our denominator. Then tan alpha is equal to L by pi dm. That will give us our helix angle of the power screw. Okay. Now this is the important thing. Helix angle is very important. Okay. Now the load W, always vertically downward. See here. Now I am talking about load here. The load is always down, I mean acting vertical, acting downward direction vertically, right? But when the load is raised, it moves up inclined plane. When the load rise, when we are rotating the handle, in clockwise direction or in clockwise direction, what will happen? The load is lifting, the load is moving up in the horizontal plane, in the inclined plane, okay. When the load is W is raised, it moves up in the inclined plane. I mean, in this is a very important thing. The full load is going to be acting in this, the threaded region only. The threaded region only, we are saying the inclined plane. See here, the threaded region is inclined plane. Now I take another figure. This is our inclined plane. Okay, inclined plane. In this inclined plane, the load is acting. While the load is acting downward direction. I mean, the load moves, when the load P is raised, the moves up inclined plane. When the load is lowered, then the load moves downward direction in the inclined plane towards downward direction. When you up, the load moves upward in the inclined plane of the nut, and not nut in the thread. Okay. Now very important. Now here, I mean that the load is raised or lowered by means of the our applied force P here. Our applied force with respect to our applied force P in the handle, lever or handle. Now, I mean the P now multiplied by dm by 2. Then how can I find out the torque? Yeah, can you tell me that? What is the torque? What is my applied torque in this? Now this is my handle. I applied the load here. This is the force P is applied on the handle. What is the torque in this now? Yeah, please tell me, boss. Hey guys, what is the torque in this case? How can I measure the torque? There's someone tell that. Hey guys. Hey, are you in the meeting? What is the torque? I see there students are there or not. Only 47 students are there. Kalyan, are you there in the meeting? Hello? Yeah, please tell someone. How can I find out the torque? See, now we able to calculate how much torque is required for lowering or rising the load W, right? That's what I'm asking. How much torque it will be required? We are applied a force is P in the handle. Bus. Someone tell me. Hmm? Hello. Hello.
Yes, sir. P into L.
P into L. Okay. Yeah. Okay. Only if you are okay, that is also correct. But now, I mean, now when we are increasing, you are very good question, very good answer. When you are increasing the lever length, we are going to apply less torque, right? With less load, less force to lifting in the weight. But only now we are not discussing about the lever design. I agree, your answer is correct. But still, you can say that if you are considering lever, then you have to consider this also, right? I mean, L plus, for example, lever length is L. I mean, our mean diameter L plus DM we have to consider. Are you clear now? Anyway, we are not discussing about lever design. I mean, whatever you are saying that correct, but the lever length plus DM as per your answer. Okay, are you clear now? Hello.
Yes, sir. Yes.
But now we are talking about, I mean, mean diameter of the screw. Mean diameter of the screw. Hence, the force, how much torque to be required is nothing but, I mean, P into dm. P into dm by 2. Sorry, here dm by 2. Sorry. P into L plus dm by 2. But now in our case, I'm not considering the lever now. P into dm by 2. P into dm by 2. Okay, this is the no. I mean, we need the helix angle. Then only we able to calculate how much a torque is required for rising or I mean lowering the load W. Lowering the load W. Okay, the load W is raised or lowered by means of the applied force P only. The load W is raised or lowered by means of the applied force P. Hence, P is acting on the mean radius, then the torque is nothing but P into dm by 2. P into dm by 2. Now I come to this. This is some of the things I would like to tell here. Now this is our see the design. This is a load acting here. This is our collar of the screw jack. This is the cup where the load is sitting here on the cup. This is a handle where we are applied the force to lowering or rising or lowering the load W. Now this is the lead, the screw movement is the lead. This is the pitch of the screw. This is the I mean here nut we are using. This is a nut on the frame. This nut is provided on the frame. Okay, and this is a mean diameter, major diameter, mean diameter. This is the core diameter of the screw. Now while rising the load, we have to give the clockwise direction rotation in the handle. While lowering the load, we have to give the counterclockwise direction of the rotation in the handle through the handle. Okay, So these are the things you can easily understand going through your book. You can easily understand now. I mean, this is the, I mean, briefly, not briefly, this is the, cleared view of the screw jar diagram here. This is a nut here, this head here, lever we are using. Okay, this is a collar. In the collar only we are where we are holding the weight. That place is called collar. Here we are accessing, in this region only we are accessing the handle to apply the force to rising or downing the rising or lowering the weight. Now I come to this multiple threads. I mean, as of now, we didn't think about thread. Only we thought about, only we discussed about the thread, single threads. Now we have to understand. Anyway, we are not going to discuss more detail about multiple threads. I mean, what is a multiple threads? Multiple threads. See here, multiple threads. I mean, multiple threads. Where, I mean, first we have to multiple threads where we are using. We have to understand first. Multiple threads, multiple threaded power screws are used in certain applications where the higher traveling speed is required. In that place we are using multiple threads. Okay, here multiple threads is nothing but two or more threads cuts side by side around the rod. Two or more threads cuts side by side around the rod. That is called multiple threads. You able to see here the multiple threads. This is a double start thread. This is a double start thread. Now, I mean, anyway, I'm going to show you a clear diagram. See here, this is single start thread. Single start thread. This is double start thread. I mean, see here, in the end, you can see here, one thread is starting here, another thread is starting here, another thread is starting here, another thread is starting here. I mean, double start thread, I mean, the offset starting position. I mean, for example, this thread is starting here. One thread is starting here. Maybe this is 0 degree. But another thread, it will start 180 degree offset. Okay, this is a double start thread. For example, this is a single start thread, double start thread. This is a four start thread. In this, you see here, four start thread. See here, I mean, here one thread is starting at 0 degree. The second thread going to start at 90 degree. The third thread going to start at 180 degree. Okay, I mean, every 90 degree it's going to start. Then the fourth thread going to start at 270 degree. I mean, this is called multi-threaded screws. The multi-threaded screws we are using where we need higher traveling speed of the nut, higher traveling speed of the screw, where it will be required. That place we are using this type of screws. Okay, I mean, see here now in single start thread, we already know the crest to crest distance is nothing but our pitch. Now see here, the pitch and length, the length of travel of the nut lead is same in single start thread. In double start thread, the L lead is equal to twice the pitch. In triple start thread, the lead is equal to, in triple start, this is a double start thread. In triple start thread, the lead is going to be 3 times pitch. Okay, I mean, here at one revolution it moves only one time of pitch, but in this case at one revolution it moves the 2 pitch. It will move the distance, the nut leading the distance, moving the distance, I mean, parallel to the axis is twice the pitch. In this case, suppose 4 start thread, this is a 4 start thread. Here the thread, I mean, that thread movement, that screw movement going to be 4 times of the pitch. 4 times of the pitch. Wherever we need higher traveling speed, those places we are using this for making power screws. Okay, now see here, and furthermore explanation about this, just to go through that you can get more information. Now see here, this is, I mean, single start thread. Just I go through that single start thread. Single start thread consists of name. This is here single, only one thread, single start thread. Okay, now here this L is equal to P. In this case, L is equal to P. Now I come to this for two start thread. Say two start thread. Here the revolution of the one revolution of this lead screw to fold two strokes of the two stroke is achieved. This is nothing but the lead is equal to twice the pitch. The lead, okay, displacement of the screw twice the pitch. The start thread is 180-degree offset, 180-degree offset, because two start thread. This is two starts thread. Okay, now come to the third start thread, the third start thread and fourth start thread. Here the each thread going to start in the rod. You see here. Okay, I mean 90-degree. This case 90-degree. 4 into 90, 360-degree. When three start thread means each thread it will start 120-degree. 120-degree. This is very important. You may expect this type of questions in the objective or competitive exam. Okay, now I come to this some of the applications where we are using. See here, I mean here we are using for car jack. While the car is getting tire is getting puncture, we are using this lifting the car and replacing the tire, right? We are using. Now see here, this we are using in car application. Now you see here in power vehicles example for lorry or bus, we are using this screw jack for lifting the vehicle to replacing the tire, right? We are using this screw jack. There are a lot of applications. Now this is the screw jack, how it will be like this, you can understand. Now I come to this one more thing. Now one more thing I missed out. I will tell you that destination, thread destination here. Thread destination is nothing but 1 minute. Keep it here. Thread destination. Thread destination. Now suppose this is for square thread destination. SQ30. SQ30 into 6 is nothing but this is a nominal diameter is 30 mm. 30 mm. This is the pitch of the screw. Pitch. This is a 6 mm pitch. This is a nominal diameter D. This is the pitch 6 mm. Now this is for square thread destination. Now trapezoidal thread destination TR. TR is nothing but 40 into 7. For example, nominal diameter 40 mm and pitch is equal to 7 mm. Okay. Now this is what trapezoidal thread. Now multi-start trapezoidal thread. Then third one is multi-start trapezoidal thread. Multi-start trapezoidal thread. In this case, now we are using TR, same notation, 40 into 14 into pitch 7. From this, we are able to understand either 2-start thread or 3-start thread or 4-start thread. How can I understand here? This is a nominal diameter D. Okay, this is our pitch. P is equal to 7 mm. Now the 14, from the 14 we are able to find out either the thread is going to be a double start thread or triple start thread or 4-start thread. Now this pitch is, now this is a lead. This is nothing but a lead. Now lead divided by P. This is going to be 2. This is a double start thread. Double start thread. Suppose, most of the threads on right hand thread. Most of the threads we are using right hand thread. Suppose the left hand thread, how can I designate? The left hand thread we are designating like this. We are putting the left hand thread we are designating like this. TR 40 into 14 7 P7, okay, in LH, sorry. LH. Now this is, whenever we are getting like this is playing in multi-start threads. Now the LH is representing that left hand threads. Now this is 2 start thread because L is 14, this is 2, this is 7, pitch is 7, then lead by P, it will give this 2 start thread, double start thread. Now, what is a triple start thread? How can I represent triple start thread? TR 40 into, now I am representing triple start thread 21 P7. Now, this is representing triple start thread 21 lead, then 21 by 7, then triple start thread. This is the way we have to use to representing the thread destination. Okay. Now, I mean, there is a disadvantages using multi-start thread. Then the efficiency of the multi-start thread is more than the single start thread. But the self-locking property we cannot obtain from the multi-start thread. Hence, when a multi-start thread is, it's mostly we are using in high-speed actuators and slice valves. In some kind of valves and high-speed actuators, we are using the multi-start thread. Okay, now I come to the torque requirement while lifting the load. Okay. See here, the screw, whatever, anyway, the basics we discussed. Now we are going to discuss about how much load to be required to lifting the screw, to lifting the weight, apply the load in the handle. Okay. Now, a screw is considered as an inclined plane. This is inclined plane. This is a screw. I mean, whatever we discussed, this is inclined plane. We consider as a screw. Again, one more time, I show you, please. See here. Then I come to here. Just a minute. This inclined plane, we are saying this screw only. We are saying the inclined plane. We are saying this is only. We are saying that inclined plane. Okay. This one. Now I come to that. Yeah. Now, see here, the inclined plane with the inclination of angle alpha, When the load is being raised, the following forces act at a point on the inclined plane. Now, this is, we know the load is always downward direction, vertically downward direction. This is the which load we want to lift, W, right? This is the P, where we are applying the effective load, where we are applying the load to lift the weight. This is effective load. Okay. Now, N is our normal reaction. This is a reaction, normal reaction at inclined plane. Okay. Now, mu N is nothing but frictional force. While we are lifting or rising the load, the frictional force is be created in this inclined plane. Inclined plane is nothing but in the nut, in the threaded portion, between the threaded portion and nut. I mean, screw and between the screw thread, between the nut thread, frictional force going to be created. That is called mu N. Okay. I mean, frictional force in opposite direction. Frictional force is opposite direction since the load is moving up. Obviously, friction force is opposite direction. Okay. Moving up in the inclined plane. Frictional force acts along the inclined plane in the downward direction. It's a friction force always acting downward direction when you are applying the load when we are trying to lift the load. That is true. You are very well known. Now, this is a schematic force diagram for while lifting the load. This is a schematic force diagram for lifting the load, condition. Lifting the load. Okay. Now see here, use this. This is a pi dm. This is a pi dm is nothing but, again I will show you, because here itself I show you pi dm. This is our mean diameter we are taking here. This is a pi dm. Okay. This is our lead. Okay. Now, consider the equilibrium. Find the equilibrium of horizontal forces. Find the equilibrium of horizontal force. This is a normal calculation. Now, what is horizontal force? This is the P is horizontal force. P is equal to mu n cos alpha. Now, P is equal to mu n cos alpha. Mu n cos alpha. Because alpha is given here. Alpha is given here. Now what is this? Now I draw a small diagram here. You can easily understand. Now this is my inclined plane. This is my inclined plane. This is my direction of. Now I am lifting the weight. This is a direction, movement. The load moving slowly in this inclined plane. Okay. Now, now I take this. I draw here. Now this is inclined plane. Now this is alpha. Okay, this is now alpha. Now, I mean the very vertical reaction force always perpendicular to the our inclined plane. Inclined plane, right? This is our load direction. Always vertical, downward direction. Now this is, now I'm taking the dotted line for here. What is this angle? This angle also must be alpha. Alpha. Now another one more line. This line is perpendicular to this axis. Now another one more line I'm going to draw parallel to this inclined plane here. Now see here. Now I would like to find out the horizontal forces. Horizontal forces. This is now our mu n into cos alpha. Mu n is cos alpha. One horizontal force. Another horizontal force with respect to this rectangle triangle. This rectangle triangle. What is another horizontal force? I mean n into sine alpha. N into sine alpha. It can be evaluated from this rectangle triangle. Okay, evaluating from this. Now n into sine alpha plus n into sine alpha. Okay, n is upward direction, n into sine alpha. This is horizontal force, equilibrium of horizontal forces. Now equilibrium of vertical forces. Vertical force is W is must equal to n into cos alpha. Now this is n is going to be n into cos alpha. N into cos alpha. N into cos alpha minus mu n sine alpha. Vertical force. Now because the mu is downward action, this direction acting, when you are taking here, this is a downward direction, mu now, then minus mu n into sine alpha. This is horizontal force, equilibrium of horizontal force, equilibrium of vertical force. Then to take these two equations, then simplify to find our P, how much load, effective load we are applying, we can get it. Now simplify these two equations A and B, we are going to get W into mu cos alpha plus sine alpha divided by cos alpha minus mu sine alpha. Now this is both side divided by cos alpha, then we are going to get in terms of tan alpha. Because now, I mean mu W into mu plus tan alpha, then 1 minus mu into tan alpha. Now, I mean, what is mu? Mu is nothing but tan pi. Tan pi. Okay, mu is nothing but tan pi. Now, pi is nothing but a friction angle. I mean, the mu is equal to tan pi. Substitute here. Mu is equal to tan pi. Substitute here. We are going to get this equation. I mean, whilst after substituting mu is equal to tan pi, we are getting P is equal to W into tan pi plus a tan alpha divided by 1 minus tan alpha tan phi. I mean, this is nothing but, I mean, what is this? This is nothing but, this component is nothing but a tan of alpha plus pi. That's alpha plus pi. Okay, this is nothing but tan of alpha plus pi. Okay, now what is, I mean, the torque, how much torque to be required? How much torque to require to rise the load? That's what our intention here. Now, what is the torque? I mean, torque mt is equal to, torque mt is equal to P into dm by 2. P is, we know now W into dm by 2 into tan alpha plus pi. This is the torque to be required while rising the load W. While rising the load W, this much torque is required for lifting the weight, W. Okay, now I come to the next case, torque requirement of lowering the load. When the load is being lowered, now this direction. The force acting at a point on the inclined plane, see here given, this is a schematic force diagram while lowering the load, W. Still W in downward direction, still the reaction force always in opposite of the, opposite, perpendicular to the plane, perpendicular to our inclined plane, always opposite, perpendicular, okay. And here, which one is changing? Only the changing the, frictional force. Only changing the frictional force only. Frictional force, only change in direction frictional force. Because when we are lowering the weight, the friction force will be acting in opposite direction. Then use that earlier calculation, whatever we discussed earlier, then we are going to find out the what is the effort, the effective force applied in the handle, we can understand. Now the effort of P, the effort of P is a perpendicular to the load W. P is always perpendicular only. Okay. Now see here, this is the equilibrium of horizontal and vertical force, whatever we calculated, same way, similar manner you calculate here. Here mu n is upward direction. Earlier case mu n is downward direction. Hence it was minus, see here, mu n, mu n here upward, downward direction, here mu n, correct only. Now here mu n cos alpha, use that earlier rectangular triangle, use that same concept, you find out P is equal, this is horizontal force, P, then P is equal to mu n cos alpha minus n sin alpha. Now n is acting, mu n is here, then n is acting this direction. Mu n is acting upward direction. Okay, now mu n plus mu n cos alpha minus n sin alpha. Vertical load. If we consider vertical load, W is equal to what? Earlier one is P is equal to what? P is now mu n cos alpha minus n sin alpha. W is equal to apply the earlier concept, n cos alpha. Now n cos alpha, this is vertical, n cos alpha, vertical upward direction, sorry, n cos alpha, this is upward direction. I erase this now. Now n is in upward direction, n cos alpha in upward direction. Okay, n cos alpha. Now mu n into sin alpha. Mu n is sin alpha. This is alpha angle, no? Alpha angle. Then alpha angle also going to be mu n into sin alpha, upward direction, then plus. Okay, plus. Now you simplify this equation A and B, right? A and B. Then finally we are going to get this equation. Okay. Dividing this numerator and the denominator of this right hand side of the equation by cos alpha, we are going to get divided by cos alpha. This is a mu going to be mu cos alpha going to be mu minus tan alpha divided by 1 plus tan alpha. Now I introduce the term mu is equal to friction angle. Mu is equal to nothing but tan pi friction angle. Then I'm introducing this instead of mu, I'm introducing tan pi. Finally, I'm going to get P is equal to W into tan alpha minus pi. This is for lowering the load. Now, what is rising the load? Rising the load, very simple. Only you have to keep in mind the symbol only. This should be a plus sign. W tan pi plus alpha. This is rising the load. This is lowering the load. This is rising the load. That's all. Now again, what is the torque? While lowering the load, how much torque to be required? WP equal to, MT is equal to P into dm by 2. Dm by 2. Then this much torque to be required for lowering the weight. Now, one more issue is that is we are going to discuss now. See here, the torque required to lower the load can be obtained by using the earlier equation, right? Now, suppose, that's what we discussed, right? Now, suppose in this case, the pi is tan pi. The pi is greater than alpha. Pi is less than alpha. Pi is less than alpha. What will happen? The value going to be negative or positive. The pi, suppose the pi is going to be less than the alpha. What is the value? Please tell me. In this equation, if I apply pi is less than alpha, what is the value of p? You no need to say the value. Either the magnitude of the p going to be negative or positive. You may consider this also, no problem. When you put pi is less than alpha, then value, the magnitude going to be negative or positive?
Negative, sir.
Yeah, thank you for your reflection. Okay, negative. I mean, now when it will be a negative, what will happen? The torque required lower the load is negative. Lower the load, like it indicates that the condition that no force is required to lower the load. Then the load itself, the load W itself will begin to turn, self-turn. With the help of the load W, that screw will be a self-turn. Then the dead weight, that weight going to be descend down. Then unless restraining the torque, okay, it is now this condition is called overhauling or overhauling, or overhauling you can say, or this condition also called back driving of the screw. Overhauling or back driving of the screw. I mean, this is very important. You may get this kind of question in any interview also. Okay. When the pi is less than alpha, that the applied torque going to be negative value, then negative value means that we don't need to apply any force on the handle to lower the weight. Then what will happen? It's meaning that even that the W itself, with the W itself, try to self W with the help of the W, with the help of the load W, the screw, the help of the W, it turned the screw and descend or lower the weight, lowering the weight, not raising the weight, lowering the weight without our control, without our hand control. Hence, what will happen? This effect is called overhauling or back driving screw. So this is not advisable in our application. Hence, we have to follow this theta pi always greater than or equal to alpha. This is important. Then the pi is always greater than or equal to alpha for creating the positive torque, because we have to create the positive torque to control our weight, dead weight. Sometimes if in this case the negative torque will be created, then due to one weight of the W, the screw getting turned, then it will be, the weight will be coming down. That is called overhauling. That effect we should not like. We don't like that effect. Hence, we should follow pi greater than alpha, greater than or equal to alpha. Hence, the positive torque is required. Now, in this case, positive torque is required to lower the load. Under this condition, the load will not turn the screw and will not descend on its own. Okay, on its own. I mean, unless effort applied load P in the handle. Okay, in this case, the screw is said to be self-locking. This is very important property. If you are not understanding, please ask me. I will explain you any number of times. No problem. Okay, the self-locking screw will while hold the load without break. The self-locking screw will hold the load in place without a brake. Here we are not applying the brake, because once we have to follow this, whenever we apply the load, the weight is lifting. Even if you leave the handle, the weight should not come down. That is called self-locking. Okay. Now, this is the very important applications. For example, they have been explained as screwdriver can jack up the car and leave the jack handle and carry out the work. In that time, self-locking is very important. Suppose no self-locking, what will happen? The car maybe fall down on his head. So that's what self-locking is very important. Okay. I mean, a screw will be a screw. Finally, a screw will be self-locking if the coefficient of friction is equal or greater than the tangent of the helix angle. Greater than or equal to the tangent of the helix angle. This you may expect this type of question in any interview and as well as competitive exam also. Okay. So any doubt, please go ahead. How many students are there? Okay. Okay, do you have any doubt, please?
No doubt, sir.
Okay. Okay. Okay, shall we continue or next class?
So next class, sir.
Okay, Kalyan. Please cooperate only Thursday. Okay, 1.5 hour. Remaining days, I will take only 1 hour. Anyway, we are going to have only 2 weeks, 2 to 3 weeks classes, right? Because we have to complete our syllabus also. Okay, come to the attendance. I will show you one video. I thought to show you one video. Yeah, guys, are you able to see the video? I once complete the video, I stop it today. Today discussion.
Yes, sir.
Are you able to see the video? Please, someone reflect.
Yes, sir.
Yes, sir.
Yes,
We
sir.
can see and hear.
I tell you one thing. This is our, I mean, nut is going to be here. This is screw here. This is handle. This is the cup. This is a collar here. Okay. In this, you can see there are a lot of screw jacks is available. You can go through that. I will share you this link also. Okay. Please go through that. Yeah, tell me, Ba. Someone is trying to talk. Okay, I take attendance, then we can leave. Roll number 1.